Hi everyone, as was mentioned, my name is Diogo. I'm the security lead at Docker. I should get away from that thing. Today I want to talk about orchestrating least privilege. But before I go into the talk, just a show of hands, amongst you, who's using Docker right now? Okay, that's expected. And of those of you that are using Docker, who's using an orchestrator? Okay, less people. So for everyone, and before I go into the meaty subject of the talk and security, we all seen this slide, right? This is the old mantra from monolithic application all the way from microservices. Our applications have been migrated towards small, loosely coupled microservices that communicate with each other. The realization here, though, is that the tools that served us on the monolithic side are no longer actually serving us on the microservices side. And so this is where orchestrators actually come into play. And this is why people start using orchestrators. And yesterday I heard that you actually already mentioned orchestrators. So today, the title of this talk is Orchestrating Least Privilege. And what this means is that I'm going to have to define what is an orchestrator and what is least privilege before I go into this. So the question is, what is an orchestrator? And before I define what is an orchestrator, I should probably, before that, define what is an orchestra. And so what is an orchestra? Well, turns out an orchestra is effectively a group of musicians that plays a particular sheet of music in synchronicity. They're all playing together, and they all come together to play a particular type of song. In this case, it's an orchestra doing a symphony. The interesting thing about arts like ballet, like operas, and like plays is that there's actually a script that they follow. You have a composer, such as Bach, and you have a conductor that is actually conducting a symphony, and you have the musicians. And even though the conductor actually has some creative liberty of how to actually do this symphony, it can't change the original script of the actual writer of the symphony, of the composer itself. So that's really interesting. It can compose how it wants, but it has to follow a predefined script. This is also true for other kinds of arts. So if you look at a play, when you're doing casting, you can change who the actual actors are, but you can't change the words that are actually being said. There is a script that has to be followed from the beginning to the end. If we go to other things like ballet, it's exactly the same thing. Even though you can change the people, you can change the set, you can change the scenery, you can't really change what is actually being done and the kind of movements that are being used. So for all three kinds of arts that I showed you here, there's one thing that is common across all of them. There is a specific script, spec. For the case of an orchestra, it's a sheet music that everybody has to follow and says exactly what you have to play. For the case of a play, it's a script that says every single thing that an actor has to say. And for the case of a ballet, turns out we actually have ballet notation. I didn't know this about ballet, but it turns out that every single movement actually has a notation associated with it. And there's an actual script that you have to follow. And you can see from the drawings there, it's actually pretty cute. And they're all showing how the dancing actually is supposed to go. I don't by any means know how to read this, but it looks to me like this actually describes exactly how the dance should be going. So this is really interesting, right? Going back to the symphony analogy, what we actually have is we have a composer, somebody creating music like Bach, and we have somebody that is a conductor that is instructing a set of musicians to actually do the music itself. If we bring this to computer science, what we effectively are going to have is we're going to have an engineer that instead of writing sheet music is going to write a spec, a description of exactly what it actually needs to execute, is going to send it to an orchestrator, which is the intermediate step, our composer here. And finally, this script is going to be executed by the servers. And the servers are actually going to run and play the music, or in this case, do whatever execution of tasks that you want. So if we go on a play-by-play comparison between what an orchestrator does and what a conductor does, you can see very easily there's a lot of commonality between the two. Number one, for a conductor, you do casting. You choose exactly what are the musicians that are going to be playing. If somebody's sick, you have to replace them. So effectively, you're in charge of membership, in charge of who's playing in your orchestra. Number two, you have to assign the sheet music to who is playing the best. if it's a tuba, you have to assign to the best player of tuba. You're not going to assign it to the violinist, right? That's pretty obvious. You also have to unify performers. So if something goes wrong, if something just goes out of whack, you are responsible to make sure that everybody's back in play and everybody's playing as one. And finally, you're also setting the tempo. So from that moment on, you're essentially like guiding people along. I think I'm doing this correctly. And everybody is essentially setting the tempo and everything is going smoothly. If we go back to computer science, you're going to see that it's very similar, a job of an orchestrator. So you no longer have musicians. And I know that servers don't get sick, but you still have to do node management. Did a node just come up? Did 100 nodes just come up? Did a node just die? You have to maintain what the membership of the cluster actually is. Instead of doing sheet music, servers don't actually play music unless you do those cool things with spinning disks. But now we're using SSDs, so you can no longer do that cool stuff. But anyway, you're doing task assignment instead of actually playing music. Instead of dealing with unexpected events that are happening while you're actually playing your concerto, you have to do cluster state reconciliation. Maybe a very important node just died, and you have to migrate all of your tasks and all of your applications to some other node in the cluster. And finally, you are also responsible for doing resource management as a job of an orchestrator. So these are the two comparisons. And now that I've talked about what an orchestrator is and how it compares to a conductor, it makes a lot of sense that I go to the next part of the title of this talk, which is least privilege. So what is a least privilege orchestrator? Before I go into a least privilege orchestrator, what is least privilege? If we go back to our analogy of the symphony, least privilege is nothing but specialization. Least privilege is the concept of a tuba player being assigned the sheet music for the tuba and handed a tuba to play. It cannot play the drums because it does not have access to the drums or the sheet music for the drums. If we go to computer science, effectively the concept of principle of least privilege means that a process must be able to access only the information and resources that are necessary for its legitimate purpose. No more, no less. Specialization. And so if you wrap this all together, and we're 17 slides into this presentation, and I'm still not done with explaining what the title of the presentation actually is, but a least privilege orchestrator is essentially an orchestrator that follows this principle that I just described in the strictest manner possible. And so this is what gets us to this title. This is what gets us to orchestrating least privilege. The obvious next question is, okay, I understand least privilege, and I understand what an orchestrator is. But why would I even want a least privilege orchestrator? Why is this good for me? Why are you insisting so much on this particular concept in security? I thought this was just for militaries and some random applications. It doesn't really have any practical use. Well, going back to our symphony analogy, least privilege is really, really useful for you to go through all of the sorts of attacker models that you want to describe and really get to an architecture that makes sense from a security perspective of your system. The first attacker model that I want to talk about is an external attacker. So in the case of an orchestra, an external attacker is effectively somebody in the audience throwing a tomato to your artists, right? They're out in the audience, they're not part of your orchestra, just effectively throwing tomatoes at you. This is an external attacker model from an orchestra perspective. From a computer science perspective, this is effectively an external attacker outside of your firewall that is trying to hack in and trying to send resources and attack your network. First attacker model. The second attacker model that we're going to have to consider from a least privilege perspective is going to be the an actual insider attacker. In this case, it's represented by a dog playing with your actual set. So in a computer science term, is somebody behind your actual firewall. There we go, got that right. So right next to one of your nodes. It does not have access to any other resources besides the fact that it is behind your firewall already and is actually accessing those resources. The third attacker model that I want to describe is the NSA cat, which becomes immediately obvious when you actually have headphones that can communicate or listen, intercept all the communications between all of your members of your cluster. The fourth attacker model that are really interesting to consider, and they're becoming harder and harder to fight against and defend against, is going to be the effective malicious musician. So effectively imagine that you have a gorilla that is now part of your symphony. you're going to have to deal with this issue. From a computer science perspective, you're going to have a malicious worker. Imagine that this is an orchestrator. The M's are managers, which are privileged in the node. They effectively are creating a consensus, running some consensus protocol amongst each other. There are the privileged nodes, and the workers are effectively less privileged nodes that are effectively just running tasks. This is when a worker is compromised, is effectively your gorilla running on your orchestra. And then the final one, the attacker model that is the hardest to protect against, is going to be the malicious conductor. Effectively, it makes no sense. There's no tempo that actually this thing is going to set such that you're going to have a nice concerto. From a computer science perspective, what that means is one of your privileged nodes in your cluster got compromised. So one of your managers over there is now under control of an attacker. So these are the 5 attacker models that I want you to consider. An external attacker, an internal attacker, somebody that is man in the middle, privileged position, and can listen or tamper or man in the middle every communication. A malicious worker, so somebody that is actually part of your set, part of your orchestra, that is acting maliciously. And you have a conductor that is actually a malicious conductor. The reason why least privilege is so interesting is in a normal setting in today's systems, people look at something like this and say, this is game over. I already have access to one of your privileged nodes. The cluster is doomed. When in fact, if you're thinking least privilege, the only thing here that a malicious attacker compromising that particular red node over there should have access to is doing an eclipse attack on the only worker that communicates with it. It should not be able to gain leadership of the cluster. It should not be able to actually poison the whatever consistent store that you have on the back end. And it should not be able to do anything to the other workers that are not even dependent on it. So this is why least privilege is so interesting and so important for us to actually look at, because it allows us to make really good decisions from an architectural perspective. And we should follow least privilege when you're building the underlayer infrastructure, because all the attacker models that come on top are necessarily going to be less strict than the attacker model that you have at the bottom. So now the question becomes, okay, we understand why least privilege is a good way of looking at this. We understand all the 5 attacker models. What about the current orchestrators? How far are they right now from actually considering the world in this view and protecting against all of these attacks? Well, things get thorny. If we continue with the symphony analogy, the current orchestrators are effectively a street musician. They're incredibly entertaining, absolutely worth the $5 that you put on their bucket, but they're definitely not what you want to run in production. They effectively have access to everything. They are the tuba player, they are the guitar player, they are the conductor. They do everything in one. Compromise of one of the actual roles in the system compromises everything else. They have all the sheets, they are the composer, they are the orchestrator, they are the musician. So now the question becomes, okay, how do we actually get there? How do we actually get to a system that is least privilege? And what are the high-level description or high-level goals that an orchestrator should have such that it could operate under these attacker scenarios and only compromise what actually goes away when that node or the resources that that node has access to when compromise happens? And so let's go back to our attacker models, 5 of them, and describe a couple of things that are the most important things that you should consider. Number 1. Mitigating external attacker. I think for this one, it becomes immediately obvious that this is one of the reasons why we had firewalls in the first place, right? We had firewalls because our attacker model was effectively some random person on the internet wants to attack my system. I'm going to block it. I'm only going to expose the ports of the services that I want. And if a service comes up on one of my hosts, it's behind the firewall, everything is good. So when we're talking about an orchestrator, or when we're talking about an actual orchestrator that is orchestrating containers, it could be as simple as this example Docker stack, where you explicitly have to actually expose a port such that that port becomes available to the outside world. As simple as that. Effectively does the same thing as a firewall will do, because there's an explicit action by someone, in this case your developer, saying that this service is supposed to be exposed. Note that Redis over there is not being exposed, even though they're going to be able to communicate with each other, right? External attacker model could be as simple as something like this. For an internal attacker model, things become a lot harder. Turns out that when you look at membership of a network, people essentially assume that if you're part of a network, then you should have access to all the resources in that network. And that should not be true. We're in 2016, which means that all of your services should be authenticated and authorized at a higher layer than just, am I part of the same network? What I mean by this is, imagine that you expose a service in a network. Instead of just saying this particular payments API is in the same network as my front-end web application, and therefore the web application has access to the payments API, this level of granular access is no longer acceptable. You have to come up to a layer where you're actually defining what endpoints, what HTTP verbs, what actual services are allowed to communicate with these particular endpoints. So even though you could have 3 services that are all part of the same network, they can't call arbitrary endpoints on my applications. They're all being authorized and authenticated at layer 7. So what I'm presenting here is a generic ACL that could be used for actual segmenting. For example, if you're using mutual TLS for mutually authenticated transport layer security, for authorization authentication between services, you could use an ACL like this to actually define what applications have access to what specific resource. This is a lot better than any firewall that you can put in between, and effectively is doing the higher level, a level of abstraction in terms of authorization. If we go to the man-in-the-middle attacker, that one is pretty easy. So effectively means that if you're deploying some kind of stack, all connections that are being set up are immediately authenticated and encrypted, both the control plane, but also the data plane. What this means is that there is mutual TLS or some kind of encryption that is immediately set up whenever you're accessing your Rails application, accessing the MySQL. So you don't necessarily need to care, even though you should, about the actual protocol of communication between this web app and this database, because the orchestrator takes care for you of actually setting up a network that is encrypted by default. Continue through our attacker models. 2 left. Malicious worker. Somebody compromised one of your nodes and it has complete access to this node, all the resources of this node. Well, things start getting a lot harder here, right? But the main concepts now are going to be around effectively mitigating and segregating what access the attacker actually has inside of your cluster. And what that means is, number 1, the attacker should not have access to anything else but what's running on this particular server. Number 2, if it is a worker, it should not be able to modify the cluster itself. So communicate back to these privileged nodes and actually change anything in the cluster. And then number 3, a node should have an identity that is assigned by the cluster and can never be modified. It is assigned, not requested. So if we generalize this, what this ends up looking at is something like a push model versus a pull model, where your unprivileged workers that are at the bottom don't have the ability of asking for anything. They're handed everything down. If you want to execute a task on a worker, bundle the resources and the secrets and the configs that I need to run this task. Do not send me some hint of something that I need to go get from my environment. So effectively bundle everything, send it to me, and only send it to me if I'm supposed to run it. And now we get to the hardest attacker model to actually defend against, which is mitigating a malicious manager. Remember, in this case, one of your core fundamental pieces of infrastructure, which is part of your consensus protocol, one of your managers, is completely compromised. What can you do? Well, now it gets really, really, really hard. But it's still possible for you to prevent a malicious attacker in this situation from having a completely catastrophic impact in your system. And the things that you're going to need to do are going to be relying on external systems for trust. So number 1, you have to get the ability of signing code with the trust anchor that is outside of your system. And what I mean by this is that the code that is executed on the workers cannot be signed by the manager itself. So the manager says, execute this piece of code, but it can't sign it. It can't say, this is a piece of code that is valid. Some developer has to sign it and do it himself or herself. Second one, no access to key material. This is a really hard one, but effectively what this means is when you're sending a job to a worker and you're sending secrets or key material that the worker needs to operate, the manager itself should not have access to actually plain text of the secret itself, and it should not be in the way. So there should be somewhat end-to-end encryption of the secrets that are being delivered towards a worker. The manager should never have the ability of spinning up new nodes. And the reason for that is if you spin up a new node under your own control and you assign a task to yourself, then you're going to have access to all the secrets and all the tasks that are being scheduled. And the final one, there should not be ability for the manager to effectively read the communication between these workers. The major thing here is that this is always going to depend on external system. So your developer is going to ultimately be, or your engineer or your ops person, going to be the person that is going to sign what the spec is, what the description of what is supposed to be running, and all the workers are going to have to independently validate it. This is really important and is one of the few hopes that you have of actually getting to a system where the manager can be untrusted. So now let me talk to you about Swarm and about why I've been thinking a lot about least privilege orchestrators. So while building Swarm, there's a lot of decisions that we had to make. Always there's a trade-off between ease of use and security. And so we really wanted to go with the motto of secure by default and continue the motto of Docker, which is everything is really easy to use. So there are two things that I think are really key to why Swarm right now is one of the most secure orchestrators out there, and that I think you're going to like and you're going to find that is actually like really well thought out and easy to use. And number one is a CA. To start a Swarm cluster, you have to essentially run one command. You do Docker Swarm init. If you've used Swarm after 112, you've seen this. And then once you do that, you effectively get a token here that in a command that you can effectively copy paste to any other node to effectively have a secure introduction of a new node to the cluster. When this happens, this is an incredibly simple command, one command. When this happens, there's a lot of stuff happening in the background. Number one, the first node that comes up, the first manager, generates automatically a certificate authority for you. It's a self-signed certificate authority. With that certificate authority, it actually issues certificates for itself. Second thing that happens is when a new node actually joins the system, it gets issued a certificate. It has to prove that it has access to the system by showing that token that I show you on the actual console. But there's a secure introduction of a worker to a system, and there's now a certificate that represents this worker for the lifetime, the duration of this worker on the cluster. There's a secure identity that actually is now part of the worker that we can use then on top to do, for example, secure secrets delivery. Then after that, we can actually add new managers and you can add new workers, and all of them are going to stay out of each other's way because the certificates actually describe the role that they have in the swarm itself. So a worker will have a certificate that says, I'm a worker, and a manager will have a certificate that says, I'm a manager. And whenever they're communicating with each other, they can independently verify if they're talking to the right party or not. And then finally, now that you have node identities, and these node identities are actual TLS certificates, well, we just use it for mutual TLS. And we do mutual authentication, authorization, and actually accounting of everything that is happening on the cluster. And all the communications are encrypted by using just TLS. And note that workers are not communicating with each other. They're in isolation, so they only have one communication path up to the managers, and everything else is pushed down from the manager to the worker. From a least privileged perspective, we can actually go a little bit further. But before I go a little bit further, let me just show you the token that I was talking about. There's a few interesting things that are happening here. Number one is we really want to be ops friendly, and we put a prefix in the token that you can search on version control, right? None of us have ever put anything sensitive on GitHub, right? It's never happened before. So this effectively makes it easy for you to do a grep test and see if somebody has leaked some of your tokens. Then we actually have a cryptographic hash that is a cryptographic hash of the root CA. The reason why we add this there is so you can actually have secure introduction of the cluster. Instead of distributing the root CA certificate across all of your nodes, you just have to distribute this token. And then you can download some file that represents the root CA and validate if this is actually legitimately the root CA or not. And then finally, there's a randomly generated secret that is effectively used to prove that you have access to this cluster and that you're actually supposed to be joining as either a worker or as a manager. There's 2 tokens, 1 for each. So this is how the token works. The first thing a worker needs to do to join a cluster is effectively hand it down this token and then creates, or the first thing that it does is give me what root CA I should be trusting. But remember, the token contains the hash that is valid. So we can get from any untrusted party the root CA that we're supposed to trust, and then we validate the cryptographic hash, and we can actually start bootstrapping the whole process by using this root CA. With this root CA, we do a one-way connection, TLS, on step number 2. We generate a key pair, and we submit a certificate signing request. The reason why a certificate signing request is interesting is because it actually doesn't have any key material. So you're not leaking any private key material. You're just sending public components for a remote server to sign. Note that at this point, the manager does not have your key. The only thing it has is effectively your public key, and now is going to sign it, and is going to send you back a certificate. And so at this point, after number 3, you have your own identity that a manager created for you that is going to identify this worker for the lifetime of the worker, and the key is only yours. And you're going to use it to communicate with any other node of the cluster, and everybody knows that you're a worker node and not a manager. And another thing that we had to do is, if we're setting up a certificate authority and a PKI for you, we have to handle certificate rotation. And we have to handle certificate rotation in a transparent fashion. So we have to rotate this in the background in a way that it actually does not affect any of your production systems. So we built this into Swarm. And you can turn it all the way down to every hour, every single node of your system will effectively request a new certificate, and it will generate a new key pair. So even if the key got leaked, because it was backed up to S3 and your S3 credentials were leaked, or somebody decided to commit it to GitHub, every single hour, these certificates and these keys are going to be rotated. So the old key is effectively useless. There's no connection between the old key and the new key, and the old key is going to expire in 1 hour and can no longer be used. Same thing happens for the actual managers. And coming in a future version, you're actually going to be able to rotate the whole root of trust. So the whole CA, the whole root of trust, is going to be able to continuously rotate. And the root itself can be compromised, and you can recover from this. So no key compromise on Swarm is catastrophic, because you always have transparent key rotation. This is a really interesting key point for you to have on any cryptographic system. If we want to go take least privilege a little bit further, in the previous model, we actually had the managers that had the private key material of the CA. So they could actually indoctrinate new nodes of the system. But with Swarm, we actually support an external certificate authority, which now is responsible for making sure that node membership is correct. What this means is it goes to what I said on the attacker model of a malicious manager, which is all the managers, they can't introduce new nodes at this point, because they are dependent on a certificate authority that is external for issuing certificates. And again, since the worker does not send any key material to the managers, and the managers can only relay the certificate signing request, which only contains public information, the manager has no privilege over the worker. Cannot create new workers, cannot fake their identity, and cannot effectively do anything else but to run as an orchestrator and run as a manager. So this is a CA component. Out of the box, Docker Swarm init, and you get mutual TLS, automatic certificate rotation, and a PKI that is taken care for you. The second thing that I want to mention that is a really important thing in a distributed orchestrator or in a container orchestrator is secrets management. This is something that a lot of orchestrators don't either support or support the wrong way. And we're going to see that there's also some flaws or some future improvements that we have to do to really get to orchestrating least privilege. But in Docker 1.13, we're shipping secrets. Effectively, you can generate a random secret and just do literally a Docker secret create. When you do a Docker secret create, what this does is it sends to the manager the secret material, and then the manager is going to hold on to it, it's going to encrypt it at rest, and it's going to keep it for any container that wants to run. So going back with the sim flow, you do Docker secret create, a secret is sent to a manager, it's sent through a secure TLS connection because you already have certificates, because we already generate them in the previous step, very convenient. The second thing you're going to do is you're going to replicate the secret across all the managers. And all of this is securely transmitted and securely stored at rest. So private material never actually hits disk. And this is cool because if one of your managers dies, obviously you have redundancy on the actual secret store. Number 3, workers that are participating in the system, when they are scheduled by the managers a task that requires a secret, then they are sent the secret right before they're sent a task. So imagine that you want to run Redis or MySQL, and you have certificates to run Redis or with MySQL. Actually, Redis, I don't think, still doesn't support TLS, so let's go with MySQL. Imagine MySQL, and imagine that you actually want to provide a certificate. You literally send the certificate right before you send the task. And so when the node wants to bootstrap the container, it magically has the secret. And what it's going to do in Docker 1.13 is it's actually going to mount a tempfs volume in memory, and it's going to pretend that the secret is now a file. And your container is just going to have access to it under var run secrets. So you could effectively use MySQL, point it to this directory, and you'll have access to the secret, but that secret never hits disk, only exists in memory. is encrypted at rest on the managers and got sent securely through the mutual TLS connection that it has. And then the other interesting thing is that no other worker has access to this secret because no other worker is going to have these tasks scheduled. And you can actually control that by actually doing deployment constraints. So you could segregate a few of your nodes of your cluster to be PCI compliant, and only the PCI compliant members of your cluster get PCI compliant secrets, for example. So backing on top of the TLS, we were able to, using the node identities, have secure delivery of secrets. But now, the next question that people always ask me is, sure, you have encryption at rest, but where's the key that encrypts all the data at rest, right? That's a really good question. And it's the one that you should always ask. Well, with Swarm, we created a really simple mechanism for you to take ownership over the key. And what that means is, if in Docker you turn autolock to true, you are now responsible for managing this key. And without this key, your cluster cannot be started. However, this key is never written anywhere, and so only exists in memory. So if one of your nodes restarts, you are responsible for going in and providing the key that then unlocks the manager. And so with this simple mechanism, you either have a cluster that is locked and cannot restart by itself, but has no keys on disk, or you have a cluster that is unlocked, can restart by itself, but it has a key that is actually written to disk. But no key material of your secrets or of your raft, which is actually what the managers are using for consensus, ever hits disk at any point in time. So it's really following the principle of least privilege, and is also following the principle of secure by default, where you effectively don't have a choice whether to enable TLS, because it's always enabled for you. You don't have the choice of how you want to introduce cluster workers to your cluster, because there's only one mode of introducing with a security token. And you don't have to choose between encryption, not encryption, and how secrets get distributed, because there's only one way of doing it, and it's the right way. So there's a couple of open problems or opportunities in all the clusters out there, and in particular also in Swarm. The first one has to do with Byzantine consensus. So I think we're all familiar with Raft and other consensus protocols. Raft came out in 2011, if I'm not mistaken, or 2013. It became really successful. All the distributed systems started using it. However, we went from a place where we knew how to do practical Byzantine consensus, and we had protocols to do it, to actually having a system that only tolerates fail-stop and no longer tolerates Byzantine mode, so a malicious adversary. Unfortunately, if you're using Raft, any of the nodes participating in the Raft protocol can effectively cause leader elections over and over and over again. And this is also true for things like that do node membership that are using, for example, Swim that is using Busty. So whatever you do, these systems are not concerned with malicious attackers that are part of the actual consensus protocols. They're only concerned with, did a manager just stop operating or not? And so this is something that as a community of distributed systems developers, we have to fix. We should get to the point where there are easy frameworks, and there's already a few out there, like Tangaroa, that provide us Byzantine consensus, because this is something that we need to get to least privilege orchestration. We need the nodes that are part of the consensus protocol not to trust each other, or for us to have a majority of 3f+1 nodes that we can actually control. The second thing is signed specs. I don't know of any orchestrator that does this right now, but the concept is, right now we have specs, and a lot of these orchestrators have them, but no engineer is actually signing it with their own private key. And no host is actually verifying it, and to make sure that this actually came from an engineer. What this means is that right now, whatever orchestrator is in here, in this case is Swarm, it could technically make up whatever it wanted to run on a worker and just send it down, and the servers and the workers will just eat it up and just start running whatever. We have to prevent against this. We have to prevent against the execution of arbitrary code. And for Swarm, we already support something called Docker Content Trust that does image signature. So you can already enable it on the actual workers and force the manager to never execute code unless it's signed by a developer. But unfortunately, the same is not true for the specs right now. And the third one is end-to-end secrets. I described how we're actually doing secrets distribution. However, in our case, Swarm still has access to plaintext secrets from a manager perspective. But what we actually want is we want a secret that is encrypted before it goes into the orchestrator, and it gets decrypted only on the actual host that it's supposed to be executed on. So it should be end-to-end. It should be executed only when it needs to and erased immediately after. There's a couple of ways of doing this. One of them is obviously encrypting towards the certificate of the node. And another way is, for example, for you to use an external system like Vault, and then you'd have a connection that is over here on the side, and the orchestrator just sends you a reference, and then the secret comes from another channel. But we have solutions for this. Nobody has built it in. And the major issue is if you want a solution by default, then you have to trust someone. And for us, who we trust is Swarm managers. And so for Swarm, we are no longer a street performer. If we go back to our symphony and our music analogy, we're not a street performer. We actually have least privileged musicians. So our workers are actually least privileged at this point. However, we're kind of like a jazz band, right? So everybody has their instrument, but we're not really playing in synchronicity. There's no actual conductor that is operating this as a band. And as a developer and as an ops person, you should not be satisfied with the state of your orchestrators, whether they are street performers or even jazz bands. And what you should really be aiming for is for an orchestra and the perfection of actually having a conductor that orchestrates everything for you in a magic fashion. This is my talk. Thank you very much.